Section 5.3 is Riemann sums and definite integrals. So what we're going to do is connect now the idea of the area, which we found in section 5.2, with the idea of an antiderivative, which we saw in section 5.1. How are those two things connected? So it says, recall in section 5.2, we estimated the area beneath the curve of f of x on a closed interval AB using n rectangles with width delta x, which was the right endpoint minus the left endpoint divided by n. And then to find the height, you picked some x value in the given interval and you plugged it into the function. So the height was determined by the function value. So it says adding the area of these rectangles, so this is the height times the width, so that would be the area of one rectangle, but then you have to add all n rectangles together. Said provided us with an estimate of the area beneath the curve. So that's the examples that I was doing that I made up for you with the nicer numbers. But then we considered, how do we make it more accurate? And that was if we let the number of rectangles approach infinity. So we looked at the limit as n goes to infinity of that sum of the areas, and that gave us the exact area right there. So that's the definition for the exact area beneath a curve on the interval from a to b, with delta x being b minus a over n. It's the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I, again x sub I is any point in the interval, times delta x, and again delta x is b minus a over n. So now it says we now extend the idea and introduce the definite integral. So what is the definite integral? If f is defined on an interval, closed interval ab, the definite integral of f from a to b is given by, well look, it's just another way of writing exactly what we've done. So a definite integral, the only difference between an indefinite integral, which is what we saw in 5.1, and section 5.3, which is a definite integral, is now you have a lower limit and an upper limit. So when we see the integral from a to b of f of x dx, what they're really asking for is what is the area beneath the curve of f of x in the x-axis bound by x equals a and x equals b. And we know how to find that exact area using the limit as n goes to infinity of the sum of the areas, right? The heights times the widths. And again, here it's just stating that delta x is your b minus a over n, and that x sub I has to be some point in that sub-interval. So, let's read this last theorem down here. It says, if a function is continuous on the closed interval ab, then f is integrable on that closed interval. So we know we can find the area. It exists. Okay, so as long as it's continuous, we can find that integral on that interval. Okay.